Hello everybody, I'm Liadys, and my role within the E3 project the last 3 years was to carry the research on the P-glycoprotein modeling. My host institution is the National Institute of Chemistry in Ljubljana, Slovenia, and my supervisor is the Professor Marjana Novič. The P-glycoprotein is a transmembrane transporter. The main function of this protein is to pump out of the cell a big number of compounds. It is important in the ADMET processes because it affects the pharmacokinetics and it also mediates the adverse drug-drug interactions. PGP has a protective function in the body against toxic compounds and is also involved in the multi-drug resistance phenomenon. So the structural analysis of PGP with its substrates or inhibitors is very important for a successful drug development or toxicity assessment. In fact, in 2010, the International Transporter Consortium was formed with the aim of identifying clinically relevant transporters and also to determine suitable in vitro or in vivo methods as well as computational models to characterize the transporter-drug interactions. The role of transporters is starting to be recognized as a big kinetic determinant and also as an essential piece of information in animal-free chemical risk assessment. So, regarding the structure of the PGP, this is formed by two homologous parts, each consisting of a transmembrane domain formed by 6 helices, as you can see here in the topology diagram, and a cytosolic nucleotide binding domain. These two parts are coupled by a cytosolic linker region. The transport mechanism is not yet completely elucidated, but the most accepted hypothesis for explaining the transport cycle is that the PGP isomerizes between two basic states, an inward-facing states where nucleotide binding domains are separated, and an outward-facing states where nucleotides binding domains are dimerized. In the inward-facing state, the active conformation of the protein, there's a high affinity to bind substrates, so the two halves of the PGP, they move to modulate the drug binding cavity. In this way, the PGP is able to capture substrates of different sizes. The first stages of the process involve the association of substrates to high affinity binding sites and ATP binding to the nucleotide binding domains. These two processes are coupled, so this is evidenced by the ability of substrates to stimulate ATP hydrolysis. Without a substrate, the PGP has a very low basal ATPase activity. The binding of the ATP causes the dimerization of the nucleotide binding domain, so the transporter isomerizes to the outward-facing state, and the drug binding site is rearranged, so the affinity for the substrate is lower, and this results in the substrate's release out of the cell. In the outward-facing conformation, then, the two ATP molecules are bound to stabilize the nucleotide binding domain's dimer. So then when the ATP hydrolysis occurs, and this can occur at one of the two nucleotide binding domains, this resets the transporter to the inward-facing state. So the first part of my work consists in the development of a classification model of PGP interacting compounds. The objective of this work was to develop a multi-class classifier able to differentiate between substrates and inhibitors, and not only between active or non-active compounds. Also, another objective was to develop an efficient in silico screening tool which could be used without much effort in drug discovery and toxicological assessment processes. The classification model was developed using the counterpropagation artificial neural networks, and 3 classes of compounds were included for the modeling. So these classes were the inhibitors, the substrates, and the non-active compounds. Here we have the workflow followed for building the model. The data set was retrieved mainly from the ADMET-SAR database, but also from other literature sources. 2D molecular descriptors were used. These descriptors were normalized using this formula, and in the end, 1,229 descriptors were calculated. The global data set was divided into training test and validation set based on clusters formed on the top map of the cojones neural network. The validation set was selected and excluded during the model construction and optimization procedures. Then the number of descriptors was reduced in order to eliminate the uninformative ones and to prevent the models overfitting. For this purpose, also the cojones top map was used. After this step, the feature selection was performed on the final set of 96 descriptors using the genetic algorithm coupled with counterpropagation artificial neural networks. So these are the final list of descriptors selected for the model, and these are the parameters of the network for the final model. So for the evaluation of the model performance, we used a confusion matrix. This matrix is also known as an error matrix. Each row of this matrix represents the instances in a predicted class, while each column represents the instances in an actual class. From this table, we can calculate other metrics like sensitivity and specificity. And also, based on this, we can calculate the non-error rate and average precision. The global performance of the model was evaluated using the non-error rate and average precision indices, while the performance of the model on each specific class was evaluated using the sensitivity, specificity, and Matthews correlation coefficient. So based on these indices, the model has a good classification performance. We can also see here in these plots the performance of the non-error rate and the average precision according to the number of epochs used in the optimization procedure. Here we have the distribution of the objects in the top map of the network. The compounds, the red squares indicate the compounds belonging to the specific class. The separation of the classes was good because each class is clustered in different regions of the network. However, a complete separation wasn't possible even with larger networks due to the high structural similarities between the compounds belonging to different classes. This work was published in May last year in the Molecules journal, and the model was recently implemented into the last version of the VIGA QSAR software. So if you are interested in trying it, you can download a beta version using this link, and it's going to be soon available in the VIGA Hub webpage. The next part of my work consisted